Hi. Yeah, good afternoon, everyone. So I'm very delighted to be here to present you with very special topics, the leveraging satellite data and AI advanced earthquake preparedness. So me myself, I'm currently doing my PhD in University of Alberta. My name is Mohammed Samiul Islam. You can call me Mohammed, you can call me Samiul. And one of my colleagues, Fei Yang, she's also doing PhD, the same lab. We are currently working in Multimedia Research Center. So our research focus is based on remote sensing. So we are still learning. So maybe we can share some of our idea with you. Probably you can take some help, and then doing further study. Probably you can just think about this is how it looks like and how the research looks like. So without further discussions, we can start our presentations. It would be around 1 hour. And if you have any questions regarding the presentations, during the presentations, you can just pull your hand, and then just I can stop, and then I can answer your question immediately. And if you do not have any questions, we can also have at the end, we have question answer sessions. So whatever questions you have, you can just you can ask us, we can answer as per our capability.
Amazing. Thank you.
Welcome. So again, our professor is Irene Cheng. So she's the scientific director and co-program director in University of Alberta, and she and Professor Anup Bosu, there is another professor. They both are running MRC lab, and you can also search MRC lab in the website. It's called MRC. If you search it at Google, you can see us. And as I already have discussed, me and my Feng about whatever we have. So actually. So today's outline is initially we will discuss about the general concept of satellites InSAR data capture, and the second one will be application. The third is basic concepts, other applications using satellite and data analysis, and then the last topics is AI-driven early warning systems. We can provide some idea, but you need to research based on if you really want to do something early systems and research proposal on that. 1, 2, 4, and 5 will be discussed by me, and number 3, the basic concept on how we can use the machine learning, will be discussed by the Fei. So what types of sensors are used in satellite imaging? So we always know that there are different type of imaging techniques that we have currently. So how many types of imaging techniques and sensors that we are currently using in this world? So we have the mobile, right? Everyone we have the mobile, has the mobile, and then we have the special camera, digital camera, and there are many ways that we can take pictures. But do we know that uh, everything's need passive sensors? So what does it mean? The passive sensors means it needs the source of the light, whether it may be sunlight or maybe another source of light. So without the source of light, we cannot take the pictures. Let's say at the night, if you take a picture, if there is no light source, you cannot see anything, and that's the problem of optical imaging. We call it optical imaging. So in the satellite, we also have this kind of options. With the source of sunlight, we can take the pictures from the globe is nearly about 800 kilometers to 1200 kilometers away from Earth. So you can just imagine how the satellites is powerful to take a pictures for so far from the our world. So there is another type of sensors we can say that is active sensors. So the active sensors is basically, if I look at there, so active sensors is, if you see here, there is no source, just only satellite and just only the world that is capturing. So let's say we have only the active sensors. It can send the signal like microwave. So what is microwave? I think you all aware of X-ray machine or maybe MRI, those who are very effective in pathology industry. So they use the same technique. We do not see any wavelength or anything, but at the end there might be some reflections on the X-ray machines, or they have special sheets on that. So these echoes can be received through the radiation and electromagnetic radiations, and then we can see the specific pictures on there. And this is known as active sensor images. So we know that now there are two different type of images can be taken through satellite. So the optical satellites, as I said, there are SAR satellites as well, or maybe there are many satellites can do both the same at the same time. So what is the difference? As I said, one is passive, optical is the passive, which needs sunlights. So it should be the vertical and oblique view. Vertical means it exactly the opposite. Let's say if I am taking a picture, right? So this is a human and I'm taking a picture from here. So it should be straight like 0 degree. Otherwise the picture's quality can be less and the resolutions can be less. So the same techniques can happen here. So the thing is that we have to take a picture exactly top view. In opposite, the SAR satellites, as I already have discussed, is active sensors and necessarily side viewing. It should not be top view. It should be like around side view, could be like around 45 degree or maybe 60 degree or maybe less. It depends on the satellites, how the design and how it works actually. So there are the so this is the main difference. So how it looks like SAR and optical images. So an optical image is taken in the presence of light, as I discussed earlier, but this is just an example. So that means it is not possible to take an optical image at night. However, it retains color information, easily human interpretable, and basic index based methods can be used for pixel segmentation. So I can say that what does it means human interpretable? Human interpretable means if you see this, it looks clearly a house, right? And this is the ground, and it probably this is a golf ground. So we can easily interpret the every single objects from these pictures. So this is called is optical image, and this is also taken from an satellite. So how a SAR image looks like? The SAR image is not actually easily interpretable. You need an expert. It looks like aircraft, but it it is not necessarily be every time it should be an aircraft. It looks like there are many cars, but it doesn't necessarily be every time it will be a car. It can be different things. It can be another idea, or anything. So and what is the another advantage? It can penetrate clouds, whether it's a rainy season or it's a cloudy or even the different atmospheric conditions. We can also check the picture's quality because it doesn't need the light source. It can just send the microwave signal and receive the microwave signal. So this is known as the synthetic aperture radar. We called it these terms. You can just remember SAR, synthetic aperture radar. If you search this word in the internet, you will find thousands of papers and thousands of YouTube tutorial how the SAR looks like, why it's important. There are many things. So due to time limitations, I'll just make a quick summary. What are the advantages of a SAR image? It has all weather capability, whether it says like tsunami or cloudy or any kind of flood or earthquake or any conditions. So any conditions it can be very important. Like, and the second is that it can captures day and night. The penetration through the vegetation canopies means like it can also capture the vegetations like the vegetation field, rice crop field, the trees, and the minimal atmospheric effects, sensitive dielectric properties. It means that every single objects has a different dielectric properties. Let's say water has a specific dielectric property which has a specific number. That is the reasons we can easily distinguish the object that this is separate object from the other objects. And also it is sensitive to structure, different type of structure like river, building, roads, the crop field. We can easily distinguish between the objects. And we have different polarization technique, means different type of technique. Like we have a optical camera. When we have the optical camera, we have like nowadays we have 200 megapixel camera, and we have the different expert settings, ecos, daylight settings, night settings, different type of combinations to take the pictures quality really higher. So according to that, how about the SAR? The SAR images also has different type of quality, different type of techniques, which one of them is polarization technique. So this technique is really essential if we go further, and we'll see that how polarization can help. So polarization gives almost an outlook of a natural RGB images. As I said earlier, it can give you a very good outlook of the images. So the next question is, which frequency range are being used for satellite imaging? So uh, what does it means? Like normally, whatever we see is a very few amount. Like if you see the optical flow, which is even one less than 1 micrometer, the wavelength. I think you all are aware of what is wavelength is, and this is in between 100 nanometer to 1 micrometer. So whatever we see in this world, like with our like eyes, without helping anything, any goggles or maybe any microscopic camera or anything, we just able to see only these portions. I can say is a total 5%. So out of 100%, there are 95% waves that we can see, and that's the interesting fact. Sometimes we see that like outside of the world, there are many things that we can't see, is because of this is belongs to 95%. We can only see 5% if there is optical window, because our eyes only can captures the sunlight or maybe the other lights of source, and then the objects can reflect that light and we can see a specific positions. The So here is the electromagnetic spectrum. Visible light is shown is this one, and has wavelength on the order of nanometers. This is the nanometers and then centimeters. We can clearly see that the wavelength, which we know this lambda, and frequency we know is f. So there are 4 different bands that available on the satellites, which is X, C, S, and L. So normally none of the satellites currently are using S, because this is not necessary. So we have X band, C band, and L band. So we can clearly see the L band is the lower frequency and the higher wavelength. So higher wavelength means like this is the higher, and according to this, like if we have another options, this is the lower. So from here to here is known as the wavelength. I think we all aware of these things from our school, that from the physics or maybe some other things, that how the wavelengths work and how to calculate the wavelengths. So this is just everything's the very basic properties. Hopefully you are understanding. Do you have any questions from here or before that? And are you enjoying this?
Yeah.
Okay. If you have any questions, if you do not understand, please raise your hands. Anyway, so this is very simple things. The like we just need to calculate the wavelength to frequency. That's it. So according to our needs and requirement, the scientists design different type of algorithms for satellites, or we can say different type of wavelengths for satellites. So each band has different characteristics. I'm just going to skip these things because we have short of times. So what is the basic principle of SAR? So how the SAR works? Now we know that what is SAR, what type of image, and how it looks like, and that's a very basic idea. So with this basic idea, what is the basic principle of SAR? So the basic principle belongs to how the SAR actually measures the ground displacement or different type of objects. So far I know that you are interested in ground deformations or maybe earthquake. So if I say what is earthquake, it's just like a ground deformations. What is ground deformations? Ground, every year grounds goes down a little bit lower side of the earth, or maybe the center of the earth. The towards the movement of the center of the earth is known as the actually effect of earthquake. So how we can measure through the satellite imaging systems? As I said earlier, the satellite emits the radar. The radar antenna on a satellite shown here this is the ERS-1, the first long-lived orbiting SAR satellite launched in 1991, is both an emitter of radar and a detector of radar. A pulse of microwave radiation is emitted. This is the pulse, right? So emitted um, and towards the ground, and some of it is scattered back to the satellites, and not all, and it should be back to the satellites again. So the antenna records both the amplitude. This is the antenna. and the antenna records both the amplitude, which is known as intensity, and the phase. I will come what is phase later, of the backscattered radar. So this is the backscattered radar. A typical radar satellite makes over thousands such measurements every single seconds. You can just imagine how like how sophisticated calculations it would be, and how like it's a very expensive project as well. So in the case of ERS1, 1600, I can say 1680 backscattered measurements per second. So this is per second. So just you can imagine, so how many images can be taken within a single seconds. We do not need all of the images, we just need a few images. After processing, and a lot of things can be happen, and this radar can send the signals to the ground station. So this is the ground stations, and then we can see the images, and then they can distribute to the world. Okay, some scientists need this data set, some scientists need these data sets, so it totally depends on them. So how the radar, so if you look at, this is our world, and this is the ground swath, and this is our desired location, and the desired location is around 5 kilometer long, and this is around 800 kilometers. So you just can imagine, this is so far from the world. And this is the flight directions. Flight direction is this way. So radar just hanging around like with this direction, and then taking the picture from here. So this is just these images you can just imagine. And then now I am coming to the little bit complex scenario. So I'm just requesting all of you to give more attention to the next slide, because this could be a little bit boring, but I'm just trying my best to give you a like best idea. So anyway, so we need as I said, this is the distance between from here to here is 800 kilometers. So the radar is 800 kilometers away from the earth. So this is a traditional radar, I can say. And what should be our antenna distance, what should be like how big the antenna could be. There are some echoes. So this is a side looking radar. So the radar target is here. As I said, the optical radar should be here, right? Position is here, but this is not the optical, this is the SAR. Our concern is the SAR, right? So that's why this is side looking, means it's just going this way and taking the pictures of the earth, and this is known as SOAT, and then continuously taking the pictures in, sorry, I'm my fault. So this is the radar direction, and this way they are going. So taking the first picture, second picture, because it is continuously moving, and also taking the pictures, and this is our target. So next picture, and the next one. So now we can achieve the target. So now we have a lot more pictures. We take the single targets on a different scenario, and now we have a different type of calculations. With these calculations we can measure the how the targets looks like be, and these all measurements can be done in the ground, like what is that called, in the ground station. So what are the benefits? Like the one of the questions remains the same. If it is 800 kilometer away, like how these targets looks like so precise. uh, I don't know, like if you have these questions in your mind, let's see, just think about it. You are looking at from your roof or from your house at least a half kilometer distance to a car. Are you able to see the car number? I don't think so. Even if you look at the from 100 meter, it's really difficult for our eyes to see the very tiny particles, like from far distance. Like, so normally for a human, what we did, we just increase our eye conditions. Like maybe we can just trying to more optical lights to put in our eyes. So by increasing our focal length, how we did it, we can just increase our the petal size. So we are just increasing the focal length of our eyes, and to allow more sunlight to be in our eyes, so that we can see the objects very clearly. So the next thing is that the same principles happens to synthetic aperture radar. This is from the earth 800 kilometer to 1200 kilometers, because these questions I was asked a lot of times, like how a satellites can precisely take the pictures from so far from the earth is because of the resolutions. If we can reduce the resolutions, then we can do that. So how we can do that? I can give some example. I already gave one example with the human perceptions. Like if you cannot see like far away distance, so let's say we need to increase the focal length. So focal length means the size of the antenna, as I already have discussed. So this is the antenna. Like you see that this is the antenna. This is exactly looks like the radar ERS Sentinel-1. So this is the radar size. So let's just imagine we just need to increase the radar size. So to get a resolutions from 5 kilometer, as I already have said, we need 5 kilometer antenna. So do you think this is a possible way? Because if the antenna size is 5 kilometer, is it possible for any scientist or any industry in this world to design a 5 kilometer antenna? It's quite impossible for us. Even it is not cost effective. It like because radars need to be a vehicle to the space by another vehicle, right? Another space vehicle. So which is impossible for any radar to design 5 kilometer, any scientist in the world to design a 5 kilometer antenna, which is not even feasible, not even near future. So we need to think about some idea. We can reduce the number of uh, the the size of the antenna from 5 kilometer to 10 meter. So how we can do that? As I already have discussed, by taking a multiple pictures. Every single seconds we are taking 1680 for ERS images. So just can imagine, and this way if it is the flight direction from here to here, it could be like around 10,000 images, or could maybe 15,000 images of the same target location. We are taking all of the images all together and combine together to get the results. And this is how we can achieve resolution of 20 meter. And how this resolution works, I think this is very depth discussion. If you have any doubt, we can discuss later, or maybe you can check on the Google, like what is satellite spatial resolutions. But the basic idea is that the question is that how we can measure, how we can take an image from so far from the earth, which is really 800 kilometer to 1200 kilometer. We need a, but answer is we need a longer antenna, but it is not feasible. So we need to take a multiple pictures and then continuously taking the same target locations and the reducing the resolution of 20 meter. Now we can clearly see the building, the roads constructions, and this is how the technique works. And look at the technique and look at the scientific derivation, and hopefully this is amazing. And I found this is really amazing idea from the satellite. So the next question is that, as I said earlier, I will come to the phase. What is phase? Because we need to measure the earthquake uh, anyhow, like the effects of the earthquake and how the ground deformation works. So to understand this, we need the interferometric SAR and what is how the InSAR works. So what is InSAR? The SAR we already have known, synthetic aperture radar, and interferometric, how interferometric works, I'm coming to that point. So these images, I think for you is not difficult because we all understand these things from the school, how the lambda it works. So we all know that the lambda is the wavelength and c is the light and the frequency is f. So lambda is equal to c by f. We all know this is a very common formula from we all know from our physics. And how the distance measures? The distance is the phi lambda divided by 2 pi. What is phi? Phi is known as the phase. This phi is the actually phase. So there are two different pictures. This is called amplitude pictures and this is called phase pictures. We all aware of specific mathematical terms, which is a plus ib. I don't know, maybe you know in a different terms. It could be j, it could be x plus jb, and this is called complex number. Normally whatever number we see 1 2 3 4 5 6, this is the integer number, or maybe there are some decimal numbers. But when we have the I, and we all know that I square is equal to -1. So this is a very basic things. If you do not understand, please ask me. I will try to explain this more. So this is a complex number. So when we're talking about the phase, there are two different things. One is the phase and one is the amplitude. So regarding the amplitude, we have this is from this we can find out the amplitude from this number. So whenever the radar captures the data, it will be like around this type of number, a complex number. From this complex number we can calculate the amplitude. We can say magnitude, we can say intensity. So whatever words we use, it looks like this. It looks like there are many mountains, and we can clearly see that there are these mountains are top, like a little bit higher than the ground. But look at the face, we do not understand anything from the face, because it's just like a sometimes I remember like maybe 10 to 15 years ago, when there was no like very less amount of internet sources. We see the TV, sometimes TV doesn't have signal, and it okay, yeah, please.
I'm just wondering, the introduction of complex numbers, is that because of a Fourier transform?
Yeah, yeah, you can say that it's Fourier transform. uh,
Oh, okay. Yeah.
yeah, you can say that it's a Fourier transform. You can say it depends, because uh, my schooling is not from here anyway. So when I found some notations is different, some symbolic terms is different, but the basic things are the same. So the thing is that if we want to get the amplitude value, I think you know how to calculate the amplitude from here. It should be a square plus b square. This is the amplitude value. And when we are talking about the phase and how we can calculate the phase is theta or maybe phi. It is tan inverse uh, b by a. So this is the phase value. Phase value will be an angle value, or we can say radian, we can say degree, and this one is just a centimeter, meter, or whatever unit that you use is totally up to you, or maybe there will be no unit. Anyway, so comes to the original conditions. So we can clearly see that the wavelengths will be the same always. This is the wavelength from here to here, from here to here. This is the wavelength. So if the wavelength is the same, the frequency will be the same. If the frequency will be the same, definitely the amplitude and phase will be the same for a single radar. It will not be changed time by time. So this is a good thing that we get to get a good calculations. And from here to here, which call it 2 pi. 2 pi means 360-degree phase. So now how we can use the phase to get the ground deformations? So before that, like okay, so this is the one part of the phase. What is an interferogram? Just think about it. Phase looks random for a single image. So this is just a single image. What does it means? I said 1680. You remember the number, right? 1680 images per second. So this is one of them. So there are two types of image. One is amplitude, one is phase. So for the amplitude, we just ignore everything from the amplitude. From now on, just imagine we only have the phase images. So now we have only one. Is it human interpretable? Impossible. Where is the house? Where is the, because with this interferogram, with this single image, we do not have any intentions to find out where exactly the house, roads, etc., whatever it is. We just need to know the ground deformations, or maybe the earth conditions, or maybe any flooding conditions, or maybe any changes happen. So look at the second images. This is the second image, the same thing, right? So let's say this is phi 1 and this is phi 2. So now we have phi 1, now we have phi 2. So how about we just think about this? The most randomness disappears when differencing between two images. So let's say I get the phi 1 minus phi 2, or maybe I can use the modular sign. So whatever it is, so I have the phi final. I can say phi. So this is the phi final. So you see now it has some color. So now it is interpretable. If you look at this like purple color, these positions are in danger zone. It means that the ground is deformed a little bit lower. and the other positions are really looks good. So we do not need to see how the grounds look like, we just need to see the difference between two or multiple. It could be phi 1 to phi 2, it could be phi 1 like dot 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 phi n. So we can make a differentiation from phi 1 minus phi 2, phi 2 minus phi 3, whatever it is, but we can get these type of differentiations and we can get the results of purple color or maybe any color which you might think this is possible. So this purple means here is the ground deformations after earthquake, or maybe some natural disaster after tsunami or anything happened here. We do not know what happened because we do not have the pictures. Now we can go to the pictures of the amplitude value or maybe the Google Earth. Okay, so the next thing is that, okay, again I'm just recapping the same thing. These images, here is the, we make an InSAR images, we call them interferogram. The two SAR images are shown, amplitude on the left, this is the amplitude value, and they're both from the same area of Turkey. This is image A, image B, taken from 12 August 1999, and the second image was taken 16 September 1999, and occurred like 5 weeks. And this is the Turkey disaster. I think the earthquake, there was a very big earthquake happened on that time. The amplitude images are used to match, to align to SAR images. So like you see, we do not need the amplitude value, as I said, we just need the ground deformations value. So so these are the phase 1, like, as I said, this is the phi 1 and this is the phi 2. So now we have removed the phase from topography. Sorry, this is just ignore this part. So we are just removing the noise, different type of noises, and make a differentiation. And now we have interferogram phase A, and this is A and this is B. So now we have the interferogram. So this is human interpretable. How can I interpret? I'm coming later. But now it is understandable that there are some colors over here, maybe purple, maybe yellow, maybe this color is not fixed. This is designed by the scientist, or this is designed by the developer, or maybe the person who actually depicted it. So we can change the color, we can change anything, but the pictures, it should be looks like this. And there are many, sorry, so there are many corrections that we can do it here. And this image source is taken from Team Wright, University of Leeds, we used by their permissions. This is not copyright actually, and I will share my like presentations later, you can see from there as well. So okay, so again, now what is per pixel phase difference? So the signal actually coming back to the satellites can be visualized as a wave traveling through space, and we are interested in a single number, phase measurement, and fundamental observable array of phase difference. And what is actually phase difference? Because in previous slides, and maybe the previous slides, I told the difference between phase A minus phase B. As I said, phase means it should be in degree, it should be radian. I'm assuming that you all aware of these two units, so I'm just assuming the degree would be the best options for us to understand. So every single wave can have a single phase difference. Like maybe the pass 1 means that this is, you can imagine A, and this is imagine B from the previous slides. So it looks initially 180 degree. So the next one, we can see the phase difference is 270 degree. Now we have the phase shift is 90 degree. So whenever we just make this wave into an images, we can calculate this 90 degree, but not for all the grounds the phase difference has. Some of the positions only have the phase differences, and we can clearly is visible by the color changing. So this is how the phase difference works. So like again the questions, one more questions coming, that is, we know that the X-ray machines, MRI machines, or maybe we can see some when we go to the airport, we see there are some kind of detector machines. They all are using microwave. This is very short distance, and we can easily understand, okay, so this is a short distance, it's going and coming back, it's much easier. But understanding phase in space is a really complex calculation. I'm not going for deeper, but the very simplest way is that that this is a long distance. I can say approximate 780 kilometer, but it could be 1200 kilometer depending on satellite conditions and how the orbits this looks like be. So the single paths is always to be considered 2 pi, but actually it is not 2 pi. We just for the calculations we just taking it as a equivalent to 2 pi, and 2 pi means is in radian format, right? So when we are converting into the degree, it should be 360 degree. So the single wavelength means this is one single wavelength. We already have discussed these things, that what is single wavelength. So we always assume that this is equivalent to 2 pi, even if it is not 2 pi in regarding in the phase in defense, because sometimes there are backscatters not coming or coming. There are many noises and many problems happens. So based on these assumptions should be taken into consideration. So how the ground deformation is measured? Now we understand the phase, and also we understand how amplitude works. So now by excluding the amplitude, we only have the phase, and now we only consider about the phase to measure the ground deformations. I already have discussed the what is ground deformations, but if you do not understand, we can also understand from now on. So this is the pass one, the pre-movement. Just imagine this is the air phase from the previous slides. So the phase I can say phi 1. So this is the ground state, one ground state. So the next one you see the post movement. So this ground is moving towards the center of the earth. This is known as the ground deformations. So every year it could be 1 centimeter, 2 centimeter, or maybe there will be no ground movement. It depends on the conditions. If there is earthquake happen, it could be 10 meter, it could be 5 meter. So there are many things can be happen. So let's say this is condition is the B. So whenever we have the signal continuously sending and back scatter the phi 1, we do not have any ground deformations. As I said earlier, whenever we have the phase differences, uh, whenever we have the phase differences which is known as the phi 2, so this red portion is the phase difference. Maybe we can say 90 degree. So now we can have a clear image that these positions is drowning, means this has a deformations. Then we can tell the people that this area is not good for living currently, because this is continuously going down towards the earth, and you should remove the space, or if there is a very expensive items, then you remove the space. Already in Canada there are many companies currently working. We work for 3B Geomatics. I'm coming with that company. So they already have different type of algorithms. Let's say in Canada we have especially in Edmonton we have the pipeline for oil and gas pipeline, and this is covered whole Canada. So let's say this area goes to the pipeline, the very big pipeline, and said continuously deforming, the pipeline can be cracked, and this is to fix the pipeline is very expensive. So if we can alert the company that you should remove the pipe, or maybe use some other tools to make it little bit upper, so that you can reduce the number of the burden, or maybe they reduce the financial burden as well. So this is how we can reduce the number of human loss, and as well as reduce the number of financial burden. So it is important to note that the only way to know there has been movement of the ground is if different areas on the ground move different amounts. InSAR makes measurements of relative deformations. If the whole area move to this is moving, right? If whole area move to the by the same amount, we would not see any relative phase point. The cartoon here shows the sleeping normal falls, and we would expect that the ground would move further away from the satellite for an area directly next to the fault than an area further away. So what I'm trying to say here, we can clearly see the phase difference here is due to the ground movement. Let's say this is the full area is condition is here, and it is moving towards here, the full area, not by the only this part. Then this is the limitations of the radar cannot detect the ground movement. because like for in this case this area is not moving, this area is going downwards to the earth, so that is the reasons we can measure the deformations. So this is another assumptions. In this world it is quite impossible right now to move all world together, all the boundary together towards the earth, because we all know that through the Hubble telescope the world is expanding. I think you know about that, right? And also it's not the world, is a whole the universe is expanding, as every day is expanding with an alpha value. I forget the number actually, but this is very interesting thing. So this is another assumptions that in this world maybe some positions, maybe some grounds can be moving towards the ground, not the all. So this is how we can do the ground deformation measurements. Another way, another examples I can give, this is a satellite on first pass. If we see the A and B conditions, and the second time pass, and the B is towards the ground, and it is measured, like see the phase difference, this is the phase difference, so we can easily measure. So the most significant part to understand here, even if it is 1 millimeter, 1 millimeter we cannot even measure with our hand, right? It's a very small amount, but the satellite can measure even 1 millimeter displacement. This is really really complex calculations, but this is a really phenomenal invention, or I can say it's a like a, it's a very significant. Yeah, please.
So if it can detect such small changes, what happens if it's trying to detect changes in something like a city, where people are moving around, cars are moving around? Will it think there's constant landslides
Yeah, this is,
on roads?
yeah, if I understand your questions, you are asking about that in the city there are many cars and humans are running around, so how the satellite can capture, right? Am I
Yeah,
right? Is
yeah.
it?
Because if it's capturing a millimeter distance, then a person being there one day and then not being there the next day will look like the ground's moved.
Yeah,
Because the
no,
person's gone.
actually, so far I know that from my experience that
Yeah.
satellite cannot capture human. It can only capture the car, and there are two different type of movements. Maybe I mistakenly missed that. So there are two types of movement. One is horizontal, one is vertical. From the vertical, which is downwards, and another one is topwards, right, upwards. From the horizontal, which is leftwards, and another one is, sorry, it's rightwards, and the another one is leftwards. For the satellites we only can detect these things, no left, no right, no up. But the thing is that we can also detect upwards, but it doesn't make sense. The earth cannot be going upwards, right? So regarding the human cannot be detected through satellites, first of all, because this is the phase difference, and I don't think so human can be detected. This is just only can detect the big structure like maybe car. So let's say the car is moving here, so if the car is going down, it can detect. Yeah, it is possible to detect by the satellites. They see a car is going down towards even the pipeline and a lot of things. This is one point of view. Another point of view is that we can remove lot of objects from the images, like because the images that we are currently watching, which is like after 15 or 20 times filtering, we remove cloud, we remove different type of noises, backscattered conditions, lot of things, and which I ignore on these presentations. If you have interest, you can see in the Google, you can search the how the atmospheric effects minimized through the satellite images. So in that, the previous raw images, probably there are some noises from human as well, as but we removed all of these things because this is our not concern. With the satellite we do not have any intentions to move, to check, or to monitor any human perspective, any human idea, or any human moving, because this is a big security threats. We just only consider about the ground deformations or maybe the agriculture sectors or anything else. Other than that, if anyone is trying to do so, is a security issue. So hopefully you understand like how it works. Anyway, so coming back to the original presentations, so we can clearly see that even the 1 millimeter downwards vertical distance can be detected, and this is so precise, and this is really a significant invention, and this is, I found this is, it's really good. And what are some challenges of side looking radars? So one challenges is like I can say this satellite sensor set an angle radar. How it looks like, this is the flight directions and this is the look directions. Look direction means this is the satellite and taking pictures in this way. So if the ground slopes toward, this is the slope you see here, uh, because this mountains, it looks like this. So from the satellite is clearly visible this area, so this is a brighter. And because these slopes facing towards the satellite have bright bright, like it looks bright, like that's why. And then slope facing away from satellite show the dark backscatters. This is the dark one, and which we called it shadow. Shadow is the big issue for like satellite imaging system. By the way, this is amplitude, not the phase. So this is the amplitude. I hope you now understand what is amplitude and phase. So when I said amplitude, you can easily understand this is an intensity image. So this is an intensity image. Yeah, please.
Sorry, another question. Can you at all combine the amplitude and phase? Oh, sorry. Can you at all combine the amplitude and phase to create a diagram? Because I'm assuming the extra noise in the phase is because you're taking the modulus of the distance, as phase repeats every 2 pi. If you multiply them together, can you create an image with an even more accurate depth map?
Yeah, you are right. I think Faye will come on that. Faye can answer these questions later when we are discussing the machine learning algorithm. But from my part, um, in some of my projects, we did imply your idea that we combine phase and amplitude to get the more information, because when we are removing the phase, there are many informations could be less. That when we're removing the amplitude, we're reducing the number of parameters, we can say features. So there are some possibilities that we can get less noises if we can combine. But coming to the original presentations, I can see that we just only need the amplitude to to see how it looks like, and we need the phase. We just need to see the ground deformations. We do not have any other intentions. But when we comes to the machine learning algorithm, your idea is really good. When we are coming to the basic idea, let's say before machine learning, how we can measure, because this one 10 to 15 years ago, the machine learning algorithm was not so popular, right? Even before 2014, the object detections technique, object segmentations technique was not so popular. So at that time, how we can measure these things? This is how we can measure. So this is the basic thing. If we add the amplitude here, it is impossible for us to see this picture by our own eyes. So that's the reasons we can ignore the phase parts. But regarding the machine learning, your idea is okay, and Faye will answer these questions during her presentations as well. So from the slide, we can clearly see that uh, the ground slopes from the satellite, the radar is reflected away from the satellites, and the backscatter intensity measured at the satellite is low. So this is the shadow area. The shadow area intensity is very low, and that's why it's black. So this is the one drawback. So the next one is this one. The areas of vegetations are rough and have a bright impact. This is some kind of area, like we can say tree or maybe crops or whatever it is. So okay, so the roughness of the earth. So roughness means this is something a little bit rough surface, not the plain surface like the soil. The rough means that there are many trees or maybe the forest, whatever it is. So that's why the surface is not smooth. That's why the scatters are brighter. But if you look at the other part, this is a little bit darker. It means that it's smoother. So this is how we can interpret. And sedimentary drainage are comparatively smooth and have less breakage. So The drainage means the water systems or maybe the related to the water, so this is much smoother than this. Initially I already have discussed one important term, which is dielectric properties. For water, the different dielectric property. For trees, different dielectric property. If you search in the Google what are the dielectric properties and what is the number, you can easily see. So based on the different dielectric properties, we can have the different type of uh, backscattered. If you just think about the X-ray, our bone has a different dielectric property, but our muscles have less dielectric property. So that's why our muscle cannot be detected. Only the bone can be detected. And if there is anything broken in our in our bone, we can easily see in the paper. So this is the same theory works here actually. So how to interpret an interferogram for earthquake scenario? So I'm just going quick through with this thing. How to interpret, like to begin, uh, this is this is the pictures that we already have discussed earlier. 17 August 1998 Izmit earthquake. You can search in the Google how the Izmit. It's a very big thing, very big earthquake happened in 1991 Turkey. So to begin, to have to sure that the sign of the conversion. Uh, the last one, this is the, what is that called, the black line, is 0 millimeter range change. So from this we can understand there is nothing change. But when we're going to the more nearer to the conditions, this is the epicenter, or we can say this is the main point of the earthquake, and these areas are very far, like I don't know, like it's very few square kilometers area. This is the Sea of Marmara, and this is the flight direction, and this is the look at side, like side looking. So this is the taking picture. So this is called fringe, a combination of blue, red, and I think it's the orange color. So each fringe has a range which is called 28 millimeter range decrease. So each fringe reducing the number of 28 millimeter. So number 2 57, by this way 10 is 283, by this way is just like 567 millimeter range of decrease. But it is really impossible for us to count all the fringes together, 1 2 3 4, because each fringe means 28 millimeter displacements towards the earth. 567 millimeter is not a small amount, is a little bit higher amount than the actual displacements. It's clearly visible this there were a big earthquake happened. And this one sometimes we can say zero deformations, and this one's the center of the positions we can say epicenter, or maybe the near to the epicenter, which affected a lot, which is much higher than this. So we can clearly visible see that if you plot a profile of the cumulative displacement and represented by fringe, you can get the curve looks something like this. And note that there is a discontinuity in the pattern in the center. And around the city of Izmit, you have to repeat the analysis of the northern pattern, the central, because if you see here is going towards here, and this is the center. In the center, it's just like a zero deformations, it looks like, but if you look at the here, it's around 1.2 meter, like around 1.2 meter displacement. So this is really like a huge displacements, 1.2 meter, you can imagine, right? But just I just need you to think about it. After a earthquake, if there is 1.2 meter displacements going towards the sea, let's say it's not in the city, because you are considering the Vancouver. So far I checked, in Vancouver all of the earthquake happened, the epicenter was in the sea actually. So if anything happened inside the sea, it is not visible, like it's really not visible. Sometimes the tsunami happens, right? Because in there are many countries are affected the tsunami, so it's a very big flood. So anything happen through earthquake, the tsunami is one of the big effects. So after the tsunami there are many places flooded, and we cannot even see that how much displacement happened on this ground. So satellite imaging is one of the powerful technique to see even inside the water, and we can create this type of map. So again I'm just recapping the same idea. This is from 2008 Wales and Nevada, I just recapping the previous part. So each cycle of the fringe, this is the fringe 1, 2, 3, 4. There are total number of the 4, and the earthquake given is 4 concentric. This is a real earthquake, not by created by human. So this is a real earthquake happened with the fringe, and then we can see this 28 millimeter displacement, which is the half of the radar wavelength. This is a, I'm just ignoring this part anyway. So this is 28 millimeter displacement for each fringe. So now we have 4. We can calculate 4 into 28. But if it is 100, if it is 200, how you can calculate? It's not possible. So by this way we can call another technique which is called wrapped and unwrapped interferogram. So this is an unwrapped interferogram. We can create a single images, single fringe from multiple fringe. This is how it looks like. And this is 0.2 means this red zones is really dangerous condition, because this red zones is more displacement and the blue zone is less displacement, and the green one is not displacement. The blue zone is like the opposite directions, like going upwards, which is impossible, as I said. So you will see the value is 0. 0 means is like around green, and the red one is only if we have the displacements. Now previously it has this type of, this is called wrapped. So now we are unwrapping this. So displacement of each fringe added together to show the total displacement. So how many satellites are now being deployed for surveillance? And this is another interesting part. So from now we see that from 1991, I believe, yeah, 1991, the first satellite from EASA, ERS 1 and 2 was launched, and 2001 they both are decommissioned. It's still there in space, but we do not need their data. We do not have their data as well. Canada also sent RCM, RadarSat 2, RadarSat 1. You can also search in the internet. Japan has a specific NSNARO 2. One of the finest satellites will be launched in 2025. I think it's already launched, or maybe they're planning, which is called NISAR. It's a part of the USA and India. They're both are collecting too. And this is L-band radar and also S-band radar, because L-band is so expensive. Previously all radars are X or C-band. So these are actually L-band. L-band, Canada also said send OptiSAR images. So these images are actually expensive. If you want to get their data, you need to buy them, or maybe you need to contact with them. So the most satellites currently has this Canada and also in Japan. Okay, so we will see one video uh, because we are working with 3V geomatics. Whatever I said, whatever, if you just remember, I'm just trying my best to give you the basic idea. And from this video you can see uh, how can I do that. Okay.
Ground Probe has partnered with 3V Geomatics, a leading...
Oh, sorry. The sound is clear.
Ground Probe has partnered with 3V Geomatics, a leading provider of InSAR monitoring services, to offer customers access to data required from satellites.
Oh,
Satellite-based
okay.
InSAR can be used to detect...
Oh,
Or you can share the video with us and we can watch it after.
because normally when we share the screen, the sound is also shared, but I'm not sure why the sound is not going.
Yeah.
Let me check. Uh,
The video is on YouTube.
Yes.
Or we could watch it after next part.
Yeah, we could do that. We have two different videos. We could see the video at the end of the slide, and this video is really helpful for students for further topics. So how can, okay, so I'm just giving this part to my colleague Faye. She will explain how the machine learning will work for the satellite image.
Amazing. Thanks, Daniel.
Thank you.
Thanks, Samuel. Is my voice clear?
Yes, perfect.
Okay. So, hi everyone. I'm Faye. So let's introduce what's artificial intelligence first. Next, Samiul. Okay. So, artificial intelligence, which is AI, is the broad concept of creating machines that can perform tasks that typically require the human intelligence. This includes things like understanding language, recognizing image, and make decision, and even playing games. And here are some everyday example of AI. When you ask Siri or Google Assistant to set a reminder or answer the questions, the AI helps its assistants to understand your and process your avoid comments. And when you watch the videos from Netflix or YouTube, this platform suggests other movies or videos you might like to depending on what you searched before or what your friends searched before. And also, the robot vacuums and the self-driving cars are also powered by AI and provide the convenience for our lives. Next, please. Okay, let's take a moment to understand the relationship between AI and its popular subsets. So, machine learning and deep learning is one subset of these categories. So, we talked about how AI creates systems that can perform tasks that normally require the human intelligence. So, within AI, there is a subset known as machine learning. Machine learning is the approach that allows computers to learn from data and make decisions without being hard code or pre-programming comments. And now there is a more professional area within machine learning called deep learning. The deep learning uses structured called artificial neural networks, which are inspired by human brains. And and for today's topic, we will focus on, next please. So today we will focus on the machine learning. So machine learning is like teaching a computer to recognize patterns and make decisions on its own by learning from data. And imagine you have a huge amount of data, and instead of manually analyze it, you can train a computer to find the patterns, find the rules within the data, and makes the prediction based on those patterns. Think of it's like how we learned to recognize different animals. For example, if you see the picture of a cat, dog, or a rabbit over and over again, you can start to recognize the unique features of each animal. Like the cat always has the pointed ears, and the dogs always have snoot, and the rabbit always has long ears. And so similarly, computers use machine learning to learn from those lots of examples and get better to learn what's the features of the data, and to finally to distinguish between the animals. So this is only a general example, and in the real training process, the model will not only learn one features to make decisions. We will talk about this later. And there are two important key concepts in machine learning, the data and the algorithms. The data is the information that the computer learns from, and the data type can be image, text, numbers, or even audio, and it depends on what problem we need to solve. Most accurate machine learning algorithms needs labels of the data, which is the answer of the predictions. So this algorithm called supervised learning. And we know the data label. We know label data usually needs lots of human resource. So some unsupervised learning method also deployed. We will focus on supervised learning today. And sorry, can you go back? Yeah. Algorithms are the rules or the instructions for the computer to follow and to learn from the data to make decisions. So let's talk about how a model learns to make predictions or decisions. So this is an example of a typical convolutional neural network, which is a popular supervised deep learning algorithm. So first, we input the image into the model, and the model will first analyze analyze and extract the feature of the image using a couple of convolutional layers. Can you click it? Yeah. Features are characterized, divided from the data that can help the model to distinguish between different categories. It's like the long ear of the rabbit and the pointed ear of the cat. These are the example of features. In this process, many mathematic operations are done to help the model understand the features. The convolutional kernel was introduced here to produce the feature map. It can be regarded as the filter that keeps the core information and drops the useless information. This is one example of filters. It's an edge detection filter. You can see that it saves the edge and discard other information. A kernel is usually a 3x3 or 5x5 size matrix, and it's like a tiny window that slides over the image, which is another large matrix. As it slides over the image, it performs simple calculations at each position. It multiplies the number in the kernel with the number in the image, and that it's covering, and then add them up. So we will get the one single number for the 9 number is covered, and this new number tells us something about that small part of the image, like detecting the edge, like detecting an edge here. The kernel keeps moving across the image and repeating this process, and finally builds up a new grid of image number called a feature map. This feature map highlights the important feature from the original image. So you can see for this animal, we got the border of the edge for it, and it will help the neural network to understand the image. Yeah, next please. After the feature extraction part, the feature map will be flattened to a long 1D vector, and then will be input into the fully connected layer. This fully connected layer acts as the final decision-making component. It's combined all learned features together and allowing the network to classify the image accurately. The mathematical calculations in this step can be regarded as a matrix dot production. After applying the activation function, the CNN's output for each class is represented as a probability value between 0 and 1. So you can see it will output a one hot vector. So for this example, it means there is 20% for this image can be a dog, and 10% is a rabbit, and 70% will be a cat, and then the final result will be the highest positive one, so it will be the cat. During the training process, there is an additional step to evaluate this output. The difference between the predicted result and the actual label, which is a true class, is calculated. So this result will be known as arrow. This arrow is then used to adjust the model's parameters. It will help the model to learn better and improve the accuracy over the time. Here is a simplified version of the supervised learning classification training process. So we first input the data and extract the feature and classify this feature and output the result. Then evaluation the results and use the arrow to update the model. And then we can start next iteration that will be input the new data again and repeat the whole process. And this process will continuing update the model, and finally it will trying to reduce the error. So we will get a better model. It can accurately classify the things we want. Now that we have a big picture of how the model learns to make decisions, and let's discuss some popular machine learning algorithms that we usually use in satellite data analysis. So first one is image classification. Image classification is the process of characterizing the image into predefined classes. Here is one example. We have labeled satellite image, and we can apply one of the methods we want, like the random forest, support vector machine, which is SVM, and or the deep learning method like the CNNs. And using this method to represent the neural network in the image, then we can classify training the model and then get the classified result. And next is image segmentation. This is the process of dividing an image into the different parts. It's like a coloring game. For each color, it represents the specific object. And when processing normal life image, like the image of the cat or the other things, unlike image classification, which assign a single label to the entire image, image segmentation label each pixel in the image according to the object it represents. However, when processing the satellite data, the line between image classification and image segmentation can sometimes blur because they both process the image at the pixel level. So some classification methods like SVM and random forest can also solve the segmentation problems. So here we have some popular segmentation methods like UNet. UNet is really popular here. And K-means clustering. And K-means clustering is sometimes fix the unsupervised learning problem that you don't have the label for the data. So you can use a K-means clustering to give you a brief segment image. And we also have the, sorry, can you go back? Yeah, we also have the fully convolutional networks. And yeah, next please. Another algorithm is time series data analysis. This one is really popular in when processing the segmentation satellite image, because the satellite data always captured time series, and we can capture the change. We can do the change detection using this type of data, and in the context of the satellite data, it's about looking at how the same area change over time, and the commonly used method, including the recurrent neural network with a long short-term memory, and the temporal convolutional networks, and the random forest can also be used here. Next, please. Yeah, the pattern recognition also it's the ability of the computer to detect the regularity and the patterns in the data. This algorithm can usually be using to the change detection or the earthquake prediction problem. When applied to the satellite data, it involves identifying the recurrent features or a change in the image. We can see in this example image, the pattern of the urban expansion can be detected by observing where and how much the urban classification has increased. This can be visualized on the map, showing areas that have colored by the light color is the changed part, and the dark part is the unchanged part. And when we count the urban number in this image, it will be marked as a pattern that the urban change. Yeah, and next, Samiul will continue to introduce some applications of satellite image analysis in the industry. Yeah, thanks, Simon.
Yeah, thank you very much, Faye, for discussing the machine learning algorithms and how it works. So, like, I have a questions to all of you. That how many of
You're
you?
on mute, Samuel.
Oh, oh, sorry. Thank you very much for your presentations, like Faye. So very nice regarding the machine learning and how we can use for machine satellite images. So I have a questions for all of you. How many of you well aware of machine learning algorithms before this presentation? Only one? So how many of you well aware of the image segmentations classification technique? Have you tried this before during programming or anything? No? Anyone? You tried this before. Very good. Which one you tried?
Um, I did some basic systems research,
Okay.
and it involved a lot of um, studying structures in neural networks. So I played around with it a little bit. Yeah.
I got it. That's very nice. Like, does it looks boring for any of you? Like, make it more informations. Do you think it's good for you, right? Like, are you feeling okay? Because sometimes the new idea, the new algorithms looks a little bit boring, sometimes frustrating, sometimes it doesn't captures in my mind. So it happens. So if you feel anything, we can explain very easy way. So those who are not well aware of machine learning, I can just say, you can just imagine machine learning is something, is a baby. So now the baby who comes to the world, and he or she doesn't know like how the colors looks like. Just the mother every time says, this is red color, this is red color, this is green, this is cat, this is dog. So he or she asks a lot of questions, right? Maybe what is this, what is this, like at least 2 to 3 years she continuously asking the questions, what is this, what is this. So once she or he starts learning, and then or that they can able to say that this is what. So the machine learning is similar type of thing. So we are just continuously trying to help the machines to understand how we looks like. This is called machine learning. Let's say I'm watching you, and you are sitting here. This is my perspective. But if I'm not here, if there is a machine, how the perspective looks like. So the machine can also see you as a sitting over here in front of him. So this is how we need to train the machine, and this is how the machine learning and the depth sense is the computer vision, we can say the deep learning method, whatever it is. So in satellite images we can use all of the algorithms. If you have any interest, you can also search in the Google, and also from the slides you can go into the little bit deeper, and this is a really big area of exploration in research industry. So what are some basic industrial applications and challenges of SAR? So,
Victor, question.
yeah, please.
I wanted to ask you about something on the previous slide with pattern recognition. I wanted to know whether it can identify regularities and relationships in separate sets of data by comparing the two, or does it only apply when you're comparing stuff in the same data set?
Which slides that you are asking? This slide? Can you please repeat again? Which slides
Can
that
you hear?
are you?
Yeah, they're just deciding who's going to answer the
Oh,
question.
sorry. So which slides that you are asking before? Sorry.
This one on pattern recognition.
Yeah, can you please answer, Faye?
You're asking how to detect the change in the image, or
No, I'm asking if it can recognize patterns by comparing separate data sets, or if it has to be from one thing.
I'm not. It's not clear for me.
Okay, it's just he's just asking. I think we just need to uh, the pattern recognitions is from only one images or from multiple images. Am I correct?
No, I'm speaking in the context of say for example, instead of talking about images, we're saying about text, so text-based machine learning. And so then, would you be able to get patterns by comparing, for example, several different reports, or can you only identify patterns by analyzing them?
So it's no different. You could compile all of those separate reports into one massive data set, and so it'd be no different to just having it with one. And so it can use multiple just by the fact that even if it could only use one, you could like collate them all into one data set and use it all at once. So you can always use multiple. just by that fact.
Thank you.
Because if
Most
multiple
context, we're
sources
trying
coming
to
in.
change an area that is not really applying to it.
Not much.
Yeah,
But technically they're completely different.
okay, yeah, they're completely different.
You have to speak louder and we
Okay.
want them to listen.
Samuel, I think we have answered that question together.
It looks great. I'm just listening because it looks like that you are enjoying the presentations, and this is our target actually.
Yeah.
So
Conversation
the answers that I so far I heard is correct actually. So just like regarding the machine learning algorithms, there are many techniques because Faye just like went through a very basic concept, but when we are going a little bit deeper, then we can understand that how the actually pattern recognition works. Normally, um, you can just always imagine, like if the data set is very less, like maybe one or two images, it's really difficult for machine learning algorithms to detect the recognitions or from whatever it is. You need a very good amount source of data. um, there is another technique which is called computer vision. We like I think you well aware of this because the computer vision is nowadays very popular because Facebook is using the computer vision's template matching, if you remember. And also if you have the Google Photos, and whenever you see that you are uploading the photos, there is a similar type of patterns or similar type of face are together, and Google Photos will ask you that what is his name, what is her name, and then you can make a group of them. So this is called some kind of pattern recognitions, but in a computer vision technique. Computer visions doesn't necessarily be the machine learning algorithms. This is separate type of algorithm which is very old because computer vision is the previous. So if you just look through the computer vision technique, there are many algorithms you can find that currently Facebook, Google, and Amazon, and there are many companies like Alibaba, Taobao, AliExpress, and even including there are many number of e-shopping channels they are using this computer vision technique. But this world is now machine learning world, so they just want to convert computer visions into the machine learning algorithms to make it much faster and then get a more accurate results. Anyway, so coming back to the original questions, what are the some basic industrial applications and challenges of SAR
You're
InSAR?
mute, Samuel.
Oh, okay. So what happened? So there are water body extractions. That was my research, initial research I started. So first, let's define the water body extraction. What does it means? Because as I said, every single satellite image as the researcher has a different perspective. Let's say I want to detect only water, or maybe only the river, or maybe only the flood. Whatever the flood happens, wherever the flood happens, I can just give an alarm to the people that okay, the water is flowing too much. You can just need to well aware of these things. So or maybe we can make a water flow pattern. So in this case we only use for water body. Now you know the mass because Faye already discussed the image segmentation technique. So this yellow part is the water. So we just need to detect the yellow part from the features. The features means the satellite images. So this is an semantic segmentation technique, and then we call it fully supervised semantic segmentation technique. So this is how we can detect, but I'm not going to represent my results. If you are really interested, I'm going to share my paper with you. If you are really interested, Faye also can share, so you can read them later on. But this is one applications, and this is very popular applications in different industries that if they wants to detect the water, how they can able to do that. So the one problem with this research I found is that, just imagine if we go back to the original slides, the back to the first few slides, as I said, this is 800-kilometer distance. So very big, like very huge amount of distance that they are taking the pictures. So the each images, like this is an RGB, like you can say optical radar, and this is near SWARE, and near SWARE is similar like RGB, is a different wavelength. RGB is just our visible wavelength, and near SWARE is like a little bit higher wavelength. I forget. I think it is 1500 nanometer, and this is 700 nanometer, something like that, or micrometer. So each pictures is like around, it could be 5 kilometer by 5 kilometer, or maybe 10 kilometer by 10 kilometer. So normally when we take the picture from the mobile, what is the total size of the images? It could be like 948 nowadays HD, maybe 4K, whatever it is. But regarding the satellite images, one single images could be 5 kilometer by 5 kilometer, or we can say 5 kilometer square, 10 kilometer square, or maybe more than this. So we all know that this, if this is an image, there are many pixels. What is pixels? I think you know, because when we are using mobile, and then phone have very specific specifications that how many pixels, maybe 16 billion, maybe 17 billion. Nowadays iPhone 15 Pro Max is using probably more than 17 billion. So which we call it nits, nits. If you have interest, you can check in the Google. So the nits has a part of the pixels. So each images has many pixels. So if it is by, if it is like maybe 500 by 500 images, so there will be total number of pixels will be 500 into 500. So each pixels is a very smaller area. So even each pixels can give you a huge amount of area, at least like I can say that this is called, we call it special resolutions, maybe 30 meter, maybe 100 meter by 100 meter. Each pixels even we cannot see with our eyes. So let's say this is a single dot, you see here is hardly visible. This single dot, yellow dot, is a big area of the lake. Maybe maybe I can say pond, or maybe lake, like maybe half kilometer area, or maybe less than half kilometer area. So it depicts like a few pixels. So we can easily see that this cannot be ignored. Like maybe this is called, we called it minority positive class. Uh, just 1 minute, please. Yeah, sorry about that. So we can now understand that each pixel is very important for us. We cannot ignore this each pixels. As Faye already discussed, in image segmentation technique, there are many noises we need to remove. But if we remove the noise, sometimes pixels can be removed, and we cannot detect even the very important and significant part. And this is the part I found is very challenging. And when we are detecting the very small number of areas which is really significant, but model cannot detect properly. The second thing, oh, sorry for that. So now we can understand that each pixel is very important. So maybe it's 10 meter by 10 meter. So each pixels can be removed through noise cancellation technique. So we need to do some kind of technique to find out that how we do not ignore the minority classes. Positive class means this yellow is the water, so we call it positive class. So we should not remove the each pixels to remove the noise. We should use different type of noise technique instead, because cats and dogs classification is much easier. It's really easy, because this is optical image, and each image has very less area. But when I'm saying this is one image is 5 gigabyte, just imagine one image is 5 gigabyte, or maybe 10 gigabyte, or it could be 20 gigabyte. Even we cannot see this type of image in our computer. We need some kind of special resolution technique, or maybe some other softwares that we are able to see this type of images. Normally in our computer we can see jpg, png. This is geotiff. You can search in the internet like how the geotiff image can be viewed. So in the geotiff image is really big, it could be less, it could be really big. So it totally depends on how the users wants their image it looks like. So this is another way is incorrect labeling. If you see the label means like I just said is masking, and this yellow part is the water. But when we look at the this is just imagine this is one satellite data. This is another satellite data. Uh, by our own eyes we cannot see the level, but look at this portion. Whenever we see this, the water is clearly visible here. This one we can clearly see. So whatever we can see with our own eyes or blank eyes without any help from the expert, the model can also detect these things very easily. So this is another challenging part in the satellite, because sometimes even if it is there water, the satellites can give you the wrong data, and this can give you the wrong informations. Even if there is a water, we can say that there is no water anyway. So the last thing is that I think, oh no, this is one another part. So noise and low albedo objects. So as I said, there could be very noisy. How it could be, like in the label there is no water, you see the green red circle, but in the predictions there is water, because if the images you can see that it looks like water, but it's not water. It says like it is a crop field. So the model detected crop field as water. So this is called false detection technique. So false detections cannot be tolerated, is because of if we detect the false detections, the results accuracy will be very less, and that is the reasons that sometimes we need to do handcrafted labeling. Or maybe, what is handcrafted labeling? We use Adobe Photoshop or some other softwares nowadays available to draw the labeling parts anyway, because this is supervised learning anyway. So there are another thing is micro positive class. So I already have discussed these things, the micro, how the micro positive class works. So these are some challenges that I faced, our team faced during working in 3D geometrics regarding water body segmentations technique. So another applications is floodwater monitoring, and this is really interesting. So this is one paper that I found, which is called flood monitoring and alarm systems. So this is a precipitations and water level monitoring systems, and then we can send this to the local remote sensing center, and then we can continuously observing GIS informations and real-time data, and we can just give these informations to the flood alarm evacuation instructions to the local government, or maybe local government can create another institutions to collaborate with remote sensing researchers. So or maybe the institutions, so they can collaborate each other to give the information. So okay, this area could be flooded in the upcoming scenario, or maybe upcoming days, so you must aware of this. There are many techniques, so we can use remote sensing. So nowadays we use um, another technique. So remote sensing techniques are a little bit different than this. Remote sensing techniques can predict much aware, like much earlier than the current technique anyway. But there are some chances of false predictions as well, because sometimes, let's say, it detects that could be happened the flooded after 15 days or 30 days, but it actually doesn't happen. It could be. So there are some good things and as well as some bad things as well. So there is another thing is water quality retrieval. Water quality, I can give you real time examples, because one of my friend is currently doing research in Edmonton oil and gas oil industry, because you know that Edmonton is the biggest source of oil, the crude oil. So whenever they just do the filtering technique or different type of techniques, they just remove the rest of the residual parts to the water, and water is damaged. And even if they filter the water, or maybe whatever they call the different type of chemical technique, still this water is not good for health, because there are some microparticles are there. So sometimes these are the very remote area and we cannot go over there. So we need to know from somehow, without going there, there is only one technique which is called remote sensing technique. With the remote sensing technique, we can check, if you see the red zones is the more polluted area, and we can use a machine learning model to predict different type of areas. Let's say we have the data set and we have the labeling and masking, and then we can use ML to ML means machine learning to predict the model as well. So another one is land cover classification. This one is already used by some industry techniques, and especially in Dubai and some Middle East countries, they are also using. And this type of ground coverage, like how we want to see our industrializations or maybe civilizations in future. So this is how we can try to map our futures through the remote sensing technique. instead of taking pictures through different way. So the another technique is water resource management. Water resource management is like how the rivers flow through the bank, and then different way of and what type of effects could be done, maybe the flooded, or maybe do we need this river flow for the crops, for the farmers, and where do we need. So we need a lot of mapping and planning. For this we do not need machine learning algorithms. We can able to see, this is optical radar by the way, so we can use intensity image to design and planning this type of industrialization technique, or maybe farming technique. mm. so so next thing is earthquakes. We are coming to the last part. I'll take maximum 10 to 15 minutes more. So the earthquake is like our ground movements that occur when blocks of rocks in earth move suddenly and release energy. The energy released as seismic waves that causes ground to move. Just imagine you have two ball, which is solid ball, right? And then I'm not sure are you capable of doing that. This is really dangerous thing, but you just give your full force and just collide each other by this, and just imagine at that time what will happen. It could be break, because if it is solid, maybe made by iron, you cannot even hear after that, because the sounds could be so louder, and then there could be some kind of wave generated, which we called it the wave energy. And what is seismic wave is just energy generated by the ground surface actually. So the most earthquakes occur near a tectonic plate. Tectonic plate is a connected plate walls, because in the world there are many connected ground surfaces are there, especially in Japan there are 4 tectonic plates. So that's why in Japan there are many earthquakes happens. So wherever the tectonic plates are, these are the dangerous area. We have to find out some kind of solutions, or maybe some kind of sensoring technique over there to detect the earthquakes faster. The movement of tectonic plates breaks earth crust into a series of faults, which are breaks of the earth crust along which blocks of rocks move. So the release of energy that accompanies the movement of rock along a fault is what causes an earthquake. So basically an earthquake is the ground deformations. This sentence you always remember. So whenever there is a ground deformations, there creates an waves. So let's say if it happens in the ocean, what will happen? If it is inside, like the deepest parts of the ocean, the waves in the length of the waves in the oceans actually will be increaser, is a higher. So that's why the tsunami happens, the flood happens. So the nearest part of the oceanic, or maybe the rivers, they are flooded area. So they are in the really danger zone. If anything happen, earthquakes inside the oceanic area. So what are the earthquake locations? At the, as I said, this could be the epicenter, could be the tectonic plate, but it's not mandatory that every time it will be in the tectonic plate. But you just always imagine the most hardiest things collide each other, whether it is side by side, vertical, or maybe the horizontal. It can create shallow, and it can create the earthquakes tend to because you see that this earth collide each other and it goes down, earth deformations, and it goes to the left side. So not full of the surfaces, only the few amount. So earthquake locations, like at convergent boundaries, rock is squeezed, causing reverse faults to form. Earthquakes can be very strong and deep. So these areas, like if you see that earthquakes can be happened in this type of scenario as well. And at transform of boundaries, shear stress. Shear stress happens whenever there is a collide between vertical or horizontal movement. If there is a very strong horizontal movement, and then the shear stress happens, a wave energy released, which is called seismic wave energy, and then we can see the destruction. And what is the current situations of earthquake in Vancouver? From the data set, I'm not sure whether it is correct or wrong, because I'm taking it from Canada.ca, which is a very authentic website to get the informations. All the epicenters are far from the actually Vancouver city. So this is the Vancouver, if I'm not wrong. This is the Vancouver, and this is from the far. So this is the first time happened, which is nearly 50 to 51, and then the next time, and the third, and the fourth, almost the similar places. So why I am discussing this, I'm coming because if you want to prepare a research proposal for early warning systems, we need to know what are the things that we need to consider. First, how to detect earthquake. We cannot detect earthquake. It's impossible. Because earthquake has special things, like it will not give you the time. Let's say you see the flood is coming, right? And at least you see some, maybe 2 to 3 minutes ago you can run away or whatever, you can just see that this alarming thing. But regarding the earthquake, it happens the center of the earth, it starts from the center of the earth. So how do you know this is not possible? But there is a possibilities, the early warning systems. The early warning systems, there is one technique that currently can be used and researcher is trying, and you can also do the proposal, which is called, if we can detect the wave energy. Let's say the after the earthquake or maybe the epicenter, if we have some kind of sensors over there, then we can detect the like this wave, and suddenly whenever we have this wave, maybe we can detect the frequency is 1 gigahertz. So now we have the frequencies like really high or maybe really less. So we found this is abnormal activities. So whenever we have the abnormal activities, we can directly send to the ground information. Okay, say that now we have the abnormal activities, please aware the citizens or please aware the peoples to remove this place, because there is a possibilities the tsunami can happen or flood can happen or maybe other disasters can happen. So you should remember, you should consider about these things. So how that it looks like be, let's say we have the acoustic communication systems we already have in the ground, and underwater sensor node. These sensors can detect wave energy or seismic or whatever it is. So it can send to the signal here and the satellite, and through the satellites it can send the signal to the central station and then alert. Another, this is called underwater seismic wave sensor. So how about the ground? If this is an epicenter, I have told you what is epicenter. Epicenter is the main point of the source of the earthquake. So if this is an epicenter, we can find out the epicenters and install the ground movement sensor. With this sensor we can detect the energy and we can convert these things to this. Now the question is that how these are the techniques without the machine learning algorithm. How can we use the machine learning algorithms and satellite image to detect the earthquake? I did not depict it here. So the thing is that we can use the machine learning algorithms and we can use these all types of technique whenever we have the images and we have the phase deformations, ground deformation technique. If you remember in the earlier slides, I already mentioned how the ground deformations can occur. So let's say in this place there will be ground deformations in 2024. In 2025 it is less. By this way we can find out these positions is not good for living. So this is called early warning systems. So whenever we are talking about disaster management, I found myself, which is really hard to detect any type of disaster, uh, like whenever it happens. So that is why if it, like there's something happens previously, like in, I forget, in the Jasper, you know that, right? Jasper was fully burned out. So there are more than 500 houses. If we know that before, we should not be there, right? But this is really a challenging part for us. Any disaster we cannot predict. What we can do, we can assume, or maybe you can say we can design something so that mm, I can use this word prevention, right? So maybe we should not do some industrialization over there. So this is the technique that 3D geomatics, from the 3D geomatics from other industries approaching, because if we see that this ground surface is not good for at all, then what we can do, we can just remove all the important surfaces from there. Let's say if anything earthquake happens, if there is no buildings, what will happen? Anyway, if you look at the Japan, if you look at some Singapore, if you look at some other countries, especially in Japan, so they use different kind of techniques to design the building. So we need to rethink about the prevention instead of protection, because if we have lots of buildings like with cement or maybe the concrete, this is really dangerous for us. We need to rethink about in a different way. Our area should be localized, and so the early warning systems doesn't mean that You just predict, and then you get the results. It should be a collective efforts with all of the institutions that you have, so that it can be a very good scenario. So whatever we learned, I think it will help you uh, a lot, I believe. And I have two videos for you to make a summary, and I don't know how to play. If you can help me to play, or maybe I can play and I run the the subtitles. What do you think about it?
Well, we might be a bit short of time to watch the videos right now. Would it be
Okay.
possible to share the links with us and we
Yeah,
watch them?
I will share the link. I will share the link, and they can saw the video later. No problem. Yeah.
Amazing. Thank you. Sorry about that.
Yeah, no problem. And
I think we might have just a couple of questions, and I might start us off with your perhaps feelings about the ethical implications of AI, particularly when you talked about certain countries having satellites and particular sensors for, you know, non-renewable resources like water or oil or other things.
Yeah, first of all, like for this type of ethical, like I do not have uh, depth knowledge of this, because whenever we are using the data, it's regarding satellite or maybe any other data sets, we have we have to take the permissions. And so far I know, whenever any data is in public, they already have given you the permissions to use this type of data. If the data is not public, there is no ethical sense that you cannot use the data. It's not about satellite, it's about anything regarding the water things. And because Canada is investing a lot of money for satellite radar, for satellite imaging techniques, so some of their radar data set is not available to the public, is only available to the ground. So as I said earlier, there are many things. It could be a security issue. Whenever they're making it public, it means that they're removing all the important structure from there. So whatever we have the data, we can use the public data set without any ethical implications. This is one perspective. The another perspective is that, like maybe Faye also can share something on her opinion.
Yeah, as for my research, I was just using the public data set. It's downloaded from the, maybe you can use Google Earth engine and some sensor official websites. But the data sets downloaded from that website is a little bit blurred, blurred some personal information, and the resolution is not that high. So yeah. But for the personal data set for the industry, it's just not public, or you have to buy it for them.
Yeah, nice. Anyone have the questions?
Can I ask, the data set you got the Vancouver earthquake epicenters from, you said it was a very good place to get data from. Could you repeat that? Because I couldn't get it.
Okay, this is from canada.ca. This is the government official site. You can search in the Google, I think, current earthquake situation in Vancouver. Then probably in Google, first 3 searches you can get this data from the canada.ca. Yeah,
Okay, thank you.
and you also can find some other informations regarding Vancouver, and like what are the casualties happens, what are the effects, and a lot of things. The reason why I depicted this is because whenever you need to design or you need to write a proposal, you just need to think about the sensors. Where should I put the sensors? For Vancouver, it is really highly recommendable to put the sensors in the near to the epicenter, so that we can easily detect before it hits the ground. But not for, as I said, there are many cities around the world which is very vulnerable for the earthquake. So for them, they need ground. So the proposal could be different to different cities. Yeah, thank you.
Thank you.
Anyone else?
Any other questions? No. Okay. I think we are good from our side, and we're a bit out of time. But we're ever so grateful for your time and the preparation that went into that slideshow. Would anyone else like to express something? Hopefully.
Yeah, thank you for sharing. Thank you for sharing the research with us. It's really cool.
Yeah. Thanks to you at all, because I took a lot of time. Initially, I thought it will be like around 1 hour. Sorry for that. And we hope that you enjoy our slides. So anything you need help, you can contact with us. You can contact with our professor. If you need further research with us, you are most welcome to join. And if you want to know the more details, we will definitely share each other's. And so thanks everyone. Have a great day. Have a safe. Yeah. Faye.
Great. I think I heard you welcome emails from us if we have further questions as we're researching, doing our final projects.
Sure.
That would be amazing.
Yeah.
Thank you so much.
Thank
We'll
you.
be in touch.
Thank you very much. Bye.
Thank you.
Bye.
Thank you.
Bye.